Okay, so I'm going to create MetaMathematics 25, and then we're going to start looking at the rheology of these things. And I mean, I think the basic point here is these are tree replacements of a certain kind. Okay, basically looking at tree replacements of a certain type. Okay, so for example, I wonder whether we should. No, I think we should just look at. See, actually, this is interesting. Once we've got expressions, this is okay. So we got the idea. Okay. We've got expressions and we've got relations. Both can be statements. And right now we're using the relations, and relations provide a natural form of inference.
Yeah.
Which can be applied to expressions as well. Okay, all right. So let's go here. And we're going to be doing the pure. Okay, so this is, oops. We need to understand, it's very important to understand why this didn't work.
Yeah, I was just taking a look at that before you called.
And?
Well, I found that using just the Boolean axioms with Uniquify false, canonicalization true, they seem to be all true. I couldn't find a way to make it work with the Wolfram axioms yet.
But I think it has to be uniquified. I don't think there's any. I mean, one thing we might just try.
What happens if I make this true? Let's see.
I'm going to make canonicalization not true, canonicalization to false.
Yeah, as soon as I uniquify, even with the Boolean axioms, I also get false statements.
There's something wrong there.
And the false statements are like, you know, A and B or not B, or C or not C equals D, which is, you know, in some way, basically just A equals D. So you have these kind of, or like A and C equals D and E, or D and F. You see the problem? These are the kind of statements I get when I uniquify.
So this is all Boolean axioms, right? You're using all the Boolean axioms, is that right?
Yeah. But then yeah, TWR.
What do
Or,
I do?
sorry, TWP. Yeah.
I say axiomatic theory.
Mm-hmm. and then
Well, then I just have to put them into this thing.
change circle plus to or, circle times to and, over bar to not, and two-way rule to equal.
Why would I do that? I want to put it in here.
Hmm?
I want to put it in there, and then later on, I'm going to do that transformation. Right here,
Okay.
I want to
Yeah,
derive
that's fine.
things.
Oh, yes. Yeah, sorry, I'm jumping ahead a little bit.
Okay. So I got lots of things there. That's canonicalized to false. Let me set it to canonicalized to true.
Okay.
Well, that's interesting and useful because that's less things. And so now you say vertex list of this.
I think it's cases vertex list.
Yeah, I know.
Oh, okay. Yeah. Two-way rule. That's right.
Center, no, circle times goes to and. Circle plus goes to or, right? And overbar goes to not.
I also included two-way rule goes to equal.
Oh yeah, right. Okay. And now what are you going to tell me? You're going to tell me a bunch of these are not tautologies. Is that correct?
Yeah, let's take a look at
well, here, let's just find out. Tautology Q. Hash, comma, A, B, C, D. Oh, for God's sake. Why are some of these not? Oh, because they have E and F in them. Well, that's extremely uninspiring.
yeah. And look at that statement.
Well, something's wrong.
Now, I'll ask this, I mean, somewhat naively, just with an open mind. If this is still meta-mathematical space, could it be that still just using some axiom in isolation with nothing else, and we look at its entailment cone, we'll still get weird statements such as that one? Is that plausible? Is that,
No,
isn't necessarily?
I
You
think
don't think so?
mathematics is, no, I don't think so. I think mathematics follows from these axioms.
Yeah, I know, but this is just this one axiom in isolation with nothing else. See,
So what?
I don't know. So I mean, I'm just
No, it
asking.
should work.
It should work just in isolation.
Yeah.
Okay.
It should be capable of deriving true statements of Boolean algebra, but not false statements of Boolean algebra. So it shouldn't be capable of deriving something. I mean, these statements here are all tautologies of Boolean algebra, I believe, in that model.
Ding ding. Right.
So something is wrong with okay, that's just the first axiom. That's another axiom. So these are actually just the axioms. There are 6 of them.
Oh, great. So
very,
as soon as we get to 7, it's already garbage. Oh, oh great.
right. So,
Great.
okay, so let's look at this. So what that means, the 7th one, I would imagine would be, let's just apply all right, let's do the following. Let us take this and make then we're going to say tuples of this comma 2. Okay, now we're going to apply this thing.
Okay.
Over all of that. What? Why isn't that replacement working? That tuples, let's say there, let's say first of that, okay, is this, and now we want to replace this with this. Okay, that looks dandy, I think. So now replace takes, I thought replace had a curried form. Yeah, it does. So what am I doing wrong here? Oh, very silly me. Very silly me. There we go.
Okay. Right.
Okay, so now let's go ahead and say, we don't need the cases, we just need this.
Okay.
All right. What happened there? AB goes to CD. Okay, so what that comes from is this tuple here. Oh, there's another problem here.
Okay.
When we take the initial thing,
Yep.
we're taking two substitution lemmas, but they're identical. And I think it's getting confused that the variables in one of them are the same as the variables in the other.
Sounds plausible.
See what I'm saying? So
Yeah.
here,
Do you have an idea for fixing it?
depends on how the unification stuff works. Okay, so hold on here. Yeah, what we need to do is uniquify each of those before we even do anything. Okay. So let's just look at this case here. Okay, so what we're going to look at is yeah, I'm pretty sure this is just going to go wrong. How can that possibly be right? How can that possibly be right? Okay, let's see what this would do if we called them A1, B1.
Yeah, okay.
B1, A1, yeah.
Yeah, okay.
And let's just, for fun, let's put these in as well in case the canonicalizer steps on these.
This is very careful. Right. Ah, what?
That's garbage. Okay, so what does the substitution lemma do here? The substitution lemma takes maybe this is okay, it takes anything of that form. No, it shouldn't be able to do this. Well, let's say if we say unification false. And let's not canonicalize.
Right. Then I don't see the twos unless they're no, I don't see the twos anymore.
No, that's because we're using the twos lemma on the ones.
Okay.
Which is correct.
Okay.
Okay, but let's take a look without canonicalizing it if we have Uniquify as true. Yeah, that's garbage. That's just wrong. That's not good.
Well, these are questions for Nick. Nick,
I know.
Yeah.
I know, but we need to get them fixed because we can't do anything meaningful without that.
Right.
Okay. So let's now look at, okay. So now we're going to do axioms of the form. Let's consider binary operator. Let's start off with a single binary operator. And remember, then we're going to go underneath where we don't have, okay, so first, consider cases where we have identified the operators.
Okay.
And also consider identified constants.
Now, sometimes we have treated operators as constants.
Yeah, those are 0. Okay, so look, the constants, i.e. arity 0 operators. Okay. So now we got single binary operator. We can look at different arities here, right? So here we're going to do okay, so the first case to look at see. This case here. Okay, so these are operators. This is an enumeration of operators and those are their models. Okay. Typical examples.
Yes.
So we're going to have, let's consider things of the form blah equals A. Okay. So what we're going to have is groupings of let's say ABB center dot arrow 2. Okay, so those are the possible things that could be equal to A. Okay, so this is, so we could actually write out our axioms here as this, and then we can go hash this A blank slash at that. Okay, so those are possible axioms. Okay, so now if we believe any of this stuff, which we may not, then we can take one of those axioms let's just take
okay.
Okay. Okay, so these claim to be the derivation trees. It's interesting that one goes down to nothing there. Okay, so let's take a look at what these got here. Vertex list of hash, and then let's do our little trick here of depatternizing. Oh, that's got events as well. Well, that's a complicated mess. Okay, let's try looking at these for,
What, for one duration?
yeah.
Yeah. Wow. Quite a difference between 1 and 2. My goodness.
Okay. So these we can look at those in terms of trees as well. So let's okay, so one of these rules leads to a certain structure of mathematics in effect, like this.
Mm-hmm.
It gets remarkably complicated remarkably quickly. So let's get a sense of what those trees are actually like. Actually, we basically want okay, so let's now make that I got to read how the documentation of how this works. Okay, that's fine. Okay. Although, you know, note things here may be wrong because of unification. Okay, so let's take this expression here. And now I think I say tree expression.
Mm-hmm. Ah.
I want expression tree. I see, that's not right. Maybe it's arguments there. That's not right either. What's the default? I think that's actually right. Okay, so let's do this. Tree, what is it? Tree element label arrow, all goes to none. Okay, but then I also want to get rid of that what that means. What the heck?
What do you want?
Just to have points there at every one of those. Well, this will probably do it. Okay, that's kind of what I want. Okay, so now I want to go to this crazy thing here. What is %516 anyway?
That one.
Oh, I see the problem.
Okay.
Okay. That's interesting that there can be one like that. Wowee, these are complicated. Okay, so let's look at, let's put that 516. First, let's look at level 1. What the hell? Okay, cases of vertex onto this. Actually, that's just that. And that fine tree wants to get mapped at level 2 over those. So I claim it's this. Okay. That's the token event graph. That's the map of that. Oh. Why is find tree not working on those? Isn't that what find tree eats? Oh, I see. It's just at level 1 then, I think. Okay.
Okie doke. Okay.
That's at level 1.
So now what do you want to do with these?
Well, these are mathematical relations. I mean, this is a representation of mathematical results.
Sure. Okay. So
So,
they're just useful in their own right. Yeah.
Right.
Yeah. Okay.
And each one of these, really, we should show the labels of the leaves in different colors. The A, B, etc. should be shown as different colors of leaves.
Okay. Yes, this will be a nice visual reference.
Right, so this is then for a given axiom system, there are various kinds of mathematical results which will come out. And eventually, this is just going to splurt out mathematical results. In general, the token event graph. So we also want the branch yield graph of the token event graph, because that's going to tell us the mathematical results that are obtained at a particular moment in time.
Yeah.
Okay, so here,
Okay.
and each one of these, okay, what's the relationship of these models?
Hold on. I'm just taking a quick note. Okay. These are just little notes for when Nick comes. Okay. You were saying which models? What, from the NKS picture?
Yeah, from the
Yeah,
NKS
okay.
picture.
Yeah.
So each one of these things, so there's another NKS picture.
Well, yeah, there are many, right?
There are many, but this one in particular.
Ah, yes.
This is the one that shows this is the one that essentially we're channeling right now. We're finding okay, so it should be the case do we generate with pure substitution and initial conditions that are self-application onto the axiom, do we generate exactly the quotes true theorems here?
We need a term for the self-application back to the original axiom.
That's really bootstrapping. That's kind of what the pure self-application I think that's what it should be called, because just it starts from itself, so to speak.
I hadn't thought of bootstrapping. That's interesting.
Baron von Munchausen would be proud. Okay, so this is for these axiom systems. This is the ABB. So for example, if we do this for smaller axioms, AB, even that is not 100% trivial. Oh, that's A dot B equals A. So the axiom is okay. So the question is, what theorems does that derive?
Well,
Okay.
we can see.
We can see here. Okay, so then here, we just don't do the map find tree on that to that.
Oh no. Wait. A dot B goes to C dot D. Oh, here we go.
Yeah, it's nonsense. Yeah, these are nonsense. So Nick has to fix these. Yeah, so I mean, these are just not right. Okay, let's
If
just.
you taken a look, I don't know if you want to look at this yourself.
No, I
The
don't.
way that Nick sets up Uniquify patterns and
I'm not interested.
yeah,
You should look at it.
It's fine.
I
don't want to look at it either.
Okay, so let's just look at what this would look like. Okay, fine. And so this is now okay, so these are possible axiom systems with and now if we do, that's that one. If we do this, where we've got this and
Okay. Boop, boop, boop.
we got a lot of stuff there.
All right.
All right, so there are all kinds of random axiom systems here.
You see, can you explain that last one?
Double overbar of A dot B.
Yeah.
Well, I mean, it's just it's creating a tree that has it can have two overbars. It's not obvious why it can't have a even larger number of overbars. See what I'm saying?
But then it just goes to A. I mean, that's just saying A dot B goes to A, basically.
No, it isn't. That's you're interpreting that bar as a knot. It doesn't have to be a knot. It can be anything it wants to be.
Ah, yes, right. How narrow of me. Right. It could be anything.
Right.
Yeah, that helps. Right. Good. Right. Yeah, it could be anything. Yeah, that helps.
They don't extend. Oh well. Oh, here's a better way to do it that will make you not think it's anything in particular.
Nice.
Or you could just say, even more simply.
No, I like the frames, personally.
Well, the frames are amusing. I think they'll be very obscure to people. Okay, so now let's do this. And let's also say G goes to 0. Ah, we're not allowed to do that. Okay. Not quite sure how we introduce, well, I think we just have a constant. Yeah, which we can write as an arity 0 operator. So better would be,
Okay. Oh. Okay.
let's simplify this a little bit. Oh, actually, what I should have done here is got rid of that. Okay. So now if we go to this.
Mhm. Oh.
Okay, so that's how we can use the constants. Okay.
Okay,
So the
great.
big thing for Nick is to debug what's going on with these things. Once we've debugged that, what we're going to find is that we got these token event graphs, and we can also remove the events
Okay,
by directly joining that. And we need to know, and you can make a note of that as another thing we'll need.
sure.
We'll need to know kind of how to reduce these so that we've only got states here.
Okay.
Okay. And then we want to have the branch hill slices that correspond to, right, the branch hill slices correspond to the state of math at a particular time.
Yeah.
And then,
And you want the branch graph of the states graph, not of the token event graph. Or do you want it for the token event graph?
It doesn't really matter. We can have it for the token event graph. It's fine. We can have, let's see, there's a notion of spatially separated events here, of spatially separated tokens.
Okay.
And that notion is, if the common ancestor of two tokens is an event, then they are branch-like separated.
Common ancestor is an event, and they're branch-like separated. Yep. Okay.
Okay. So that being so, I want to understand what the space-like separated events here are, what that corresponds to. Those are, okay, so in this picture, all right, so we got another thing coming up here, which is interpretation.
You mean like observation?
No, our interpretation. So in this case, right, so these are space-like separated events, space-like separated.
Oh, like a WPP interpretation?
Yes, space-like separated tokens can coexist in a particular branch of mathematical history. But branch-like separated cannot. I need something to eat. I'll be right back.
Okay.
So the entailment cone of a lemma of a statement is everything that can be derived just from that statement. So in Boolean algebra, okay, so
And are we thinking of entailment and derivation as basically the same thing?
yes.
Yeah, okay.
Okay, so e.g., for Euclid, we have plots of what gets entailed from each of the axioms.
Mhm. Is that an apple, by the way? Is that
Yes,
what
it
you,
is.
I
Yeah.
can't, the apple is the one food to which I'm allergic. I can't eat them.
How unfortunate.
Anyway,
I went through most of my life. I mean, claim when I was a child that I was allergic to everything I didn't want to eat. That was a new idea at the time. So I believed I was allergic to nothing, in fact, in actuality. And then I realized that when I eat kiwi fruit, I get this bizarre kind of oral reaction. But I'd never really, I just thought, well, it's a weird acidic thing, so whatever. But I think I'm allergic to it. But so what? It's one of those things that's kind of so obscure.
oh yes, if you're going to have an allergy,
It's a good one
that's
to have.
quite fortunate. Yes, right. Anyway,
Okay.
just sounds like an apple. And I've been
Yeah.
eating bananas. Yes,
Okay. So then, so if we're doing group theory, for example, yeah, okay. So, e.g., in group theory, we can have entailments, i.e., statements from the general group axioms. Then we'll have more entailments if we add the specific relations of a group.
Okay.
Okay, so that's as it should be. Now, okay. Now, the question is, what are the geodesics in here? So the geodesics could be, e.g., okay, within a cone, okay. Let's see. I'm trying to think the interpretation of a point-to-point geodesic. Point-to-point geodesic. There is a single statement that leads to another single statement, to another statement, right, without needing anything else.
Without needing anything else. Yeah, okay. It's just a path between 2 points. Nothing
Yeah.
else. That's it. Okay.
Now, I think what's confusing me is that it doesn't need any particular ambient I'm saying it doesn't need ambient any ambient data. It just well, okay. Because many proofs
Mhm.
may take multiple input points, i.e. axioms, to derive a single statement. Okay, now an automated theorem proving system, again, does something even more bizarre. ATP, one normally adds in the potential theorem and sees if one can derive a tautology.
Okay.
Right, that's how it works. I don't know why it works that way, because it doesn't seem like the best way for it to work.
Adds in the potential theorem and sees if one. Yeah. Okay.
As opposed to just pathfinding, the direct way of doing it. I don't understand why it does it backwards.
Right. Yeah.
I think it has to do with the way the completions work. Oh yeah, it does. It has to do with, yes. This has to do with using completions to make the pathfinding simpler. That's why it does it that way. But I think
how difficult is it to do it the other way?
I don't know.
Well, that's
I don't think there are any known algorithms for doing it the other way, because this is using essentially Knuth-Bendix completion, aka, et cetera, et cetera, et cetera.
Yep.
I mean, there's an interesting question whether it can be done directly.
So you're given the theorem, and that reminds me of the problems in MP. I don't know if it's the same. I haven't looked into the relationship between those two.
Well, Stephen Cook's original paper was about the complexity of proofs.
True.
So
true. Yes, I know that paper. Right.
Okay. So anyway, so then we've got this point-to-point. Okay. So the statement of relativity here. So first of all, okay, another question is there confluence in these TEGs? I don't know.
No, wait. This point-to-point question, do you want to answer it, or are we just enumerating questions at the moment?
I mean, what the interpretation is?
Well, do you want to actually find an example of that?
Not really, because this data is wrong.
No, not okay. Not now, but for the blog, for the project.
Possibly, yes.
Just understanding what the purpose is of asking these questions.
Yeah, I'm trying to scope out what. Okay, so another important question: is there confluence in these?
Okay.
I think the answer is going to be yes. And then the question is, okay, then what are the reference frames?
Right.
Of mathematical development? And the
Math?
answer is they're non-time like, I mean, they're, okay, so these contain statements that can, what does it mean that they're space-like or branch-like? What does it mean that they, oh, I see. These contain statements that in what sense are they independent? That are instantaneously independent, maybe, whatever that means. So in other words, those statements may have common ancestors,
Yes.
but let's see. Well, it's something about independence. And then the other thing we can do, how are statements laid out branchially in these slices? Okay, so that's going to tell us, you know, the distance between statements. It's going to give us a layout of statements. So all the statements eventually come from the Big Bang. What does it mean when statements are far apart? Okay, when statements are far apart.
Oh, well, I mean, according to Nick's intuition, it means that at some point, one of the variables in the statement underwent some positional shift, and the actual position of that variable differs between the two statements.
Well, hold on. When statements are far apart, this means that to derive one from the other will take a while. See what I'm saying?
Fine. Yeah.
So,
But then,
in other words, these are
then-
far separated regions of mathematics.
but then is the actual distance metric just the number of operations to translate from one to the other?
Which is essentially branchial distance.
Okay.
Now, none of what we're doing here is rulal yet.
No.
That's even a bigger can of worms.
Well, by definition, yeah.
You know, I have to say that, you know, I think all of this stuff, I mean, when I'm more impressed with Democritus than I might have been, or Epicurus, or any of these guys, Leucippus, than I might have been, because it is so, you know, in modern times, we've got our computer displays, which are clearly made of discrete pixels and things, but yet they make something which is synthesized into sort of continuous reality. And in a sense, what all of this stuff that we're doing is saying underneath all of the reality that we perceive is just this incredible mess of, you know, little tiny computations that are going on.
Yeah.
And the idea, the intuitive idea, I mean, I've been saying this for like decades, but I mean, the intuitive idea, the question is, in a sort of, in the kind of psychological interpretation of all of this, it's just very weird. People
Yeah, I'm not surprised though that someone made the claim that Democritus made, right? All that has to happen is someone makes the more intuitive claim that everything's continuous, right? And then someone just has to have a contrarian spirit and disagree, right?
No,
And
but
say that they
the fact that he thought it was made from identical elements is what I find interesting.
not just the discreteness.
No, the fact that
I see.
everything with all its diversity can be made from identical elements is to me not obvious. I mean, it's very elegant, and it's what we're basically pushing here, except in a more bizarre, I mean, the Rulliad is a more bizarre. Oh my gosh. I mean, I've been discussing with Hatem the relationship between the Rulliad and God, which is,
That sounds very much like a really a Hatem kind of conversation. Yes.
well, I mean, what's interesting is a lot of these people from Spinoza, the whole
Sure.
generalized Spinoza thing, that's how it all comes out. That, you know, I mean, I don't know what the relationship is between that and the more, consumer oriented versions. So I'm
Consumer oriented what? Versions of
religion,
what?
the consumer oriented theology, where it's like,
Well, it depends on your depends on your consumers. Uh, some consumers are not thinking that hard, right?
well, maybe so, but I mean that's a different issue. I mean, the question is, oh, anyway, but okay, this is for the philosophy thing, but let's not get diverted into that right now. Okay, how are statements laid out branchially in these slices? Okay, for example, I'd like to see what it looks like when one of these things doesn't really get very far.
Oh, well,
Like, for example,
that's not hard either. Yeah. Okay.
okay, but what does it look like? What does it look like when the theory is decidable? Because I suspect, I mean, maybe these are decidable. I don't know.
Well, we have like examples of these little squares, for instance,
I,
right?
I know that. I know that. But I mean, these may be decidable as well. I don't really know. This may be, it may be going to a lot of trouble to do something which is actually reducible.
Yeah. Yeah. Well, and not that I really need to say this, but there are, of course, ways of generating these without having to actually visually render them. And then you could generate them for a higher number of iterations and you can actually see what happens.
Sure.
It doesn't really work when you try and visually render it because you run into difficulties really
Right.
quickly.
But okay. So then the next question is, how do models relate to all of this? Models as in model theory.
Yeah, this still is not that firm.
What? The model theory stuff.
How it fits into our
Well,
framework.
let's understand it. Okay. I mean,
Yes.
that's
Yes.
basically what.
Yeah, I'm not saying it can't be understood. I'm
Right.
recognizing. Yeah, yeah.
So
It's
what
been
is a
on my
model?
mind.
A model in one of these things. Okay, so let's take one of these axioms. Okay, let's take an axiom like this one here: AB goes to A. Okay.
Okay.
So let's have another section here called model theory. Actually, these ones are very nice and jolly. Okay, now conveniently we have Nick's find finite models thing.
Yes, right. Okay.
Which is a version of the thing that I had for NKS. Finite models. Here we go. Oh, there we go. There's one that's almost exactly like this. Okay, so find finite models of this case here A dot B goes to A. Well, that's exactly this one here. Okay, so there's the model. Now, does it? Okay, now what happens if we allow a larger model there?
Okay.
Oh, I see. Okay, fine. Okay, so what does that mean? That means that if we allow, what the heck does that 377 mean?
Well, what exactly does the 3 mean?
Here,
Yeah,
3 possible values, 0, 1, 2.
377. Yeah, okay.
Well, what is that? What is that? What is that? I'm guessing. Yeah, I'm guessing that's just the ID number for this multiplication table. Indices as keys. Yeah, indices for models. That's of the k to the k to the a models of our operator of arity A. Okay. Okay, so let's look at these ones here. And then we're going to understand what these, just to get a sense of what kinds of things can happen.
Great. Okay.
Okay, so let's look at that model there.
Okay. Yeah.
Okay, so that allows multiple models. Okay, and if we went to 3, we'll allow even more models.
Do these models lend themselves to visualization in any way?
Yes, you can make the multiplication tables. That's what I did in AKS.
Right. Right.
But other than that, not particularly.
No, that's fine. That's fine.
Okay, so now, okay, so what does this mean? When we have a model, when we have a specific model, it means that in this graph, in this thing here, what the heck does it mean? It means, well, okay, so each thing, okay, so at every node here, we've got a relation.
Okay. Yeah.
Let's take one of those relations, okay? Even though we think many of them are incorrect here, but okay, let's a random relation here. Just a minute. Okay. So now, okay, what would a model mean? So a model means that this relation will be true for all possible 0, 1, let's say it's a model, a size 2 model.
Okay.
If we make the truth table here, okay, if there is a model of that center dot, oops, then for every choice, for every of the k choices of each variable, the LHS and RHS will be the same. That's what it means. So it could be the case okay. So any given statement has essentially a barcode of what values its two sides can take on.
Can we see that with the multiplication table?
Yeah, we can. Okay, for this case.
Yeah.
Well, I mean, this one is nonsense because this one is just
Well,
a
let's take a
relation.
different example then. Let's
Yeah,
take an
okay.
example in which we're more confident.
Well, we can do one with NAND. Okay, let's just get a true statement of NAND, of the NAND world. A true statement of, I think I've got a bunch of those in the Euclid post.
Yes. Yes, yes. I can
But
see
let's
that
take,
image, that orange
okay,
image.
so,
Yes.
So let's take axiomatic theory of okay, so this should give NAND and NOR. What do you know? Okay, this should give nothing. Ooh, terrible. Takes a long time. Okay, and this should give something, again, if it comes back. It's the next model of Boolean algebra. And by the way, let's look at this. I've got something else to show here.
Okay. Okay.
We may want to parallelize this. I think this has a parallelizer of true. And then I want to see what finite models on that next thing does.
Well, now what?
It's running.
Okay. Okay, there it is. Yeah, okay, I see.
Well, I don't know what that was doing exactly, but
Stephen, how are
yeah.
these estimated times calculated?
Well, based on what's already happened. And the estimated time, if nothing's already happened, I don't really see how it can estimate the time, but it still seems to manage it. Okay, look at that magnificent thing.
Okay.
Okay, so those are
Yeah.
the next level results.
Nice.
Those are the next level possible models for Boolean algebra.
Beautiful.
Okay.
Can I see them in the multiplication table?
We could if we wanted to, but I mean, that's how I actually found these axioms. I pruned down by looking at these models.
How long did that take?
A couple of days.
Okay.
Once I knew what it was once I had the idea of doing it. Now I tried to do that for some other Axiom systems, and it's something we should try and do again because that was 20 years ago, 20 years ago, and there were a few I never managed to get.
You still know what they are?
Yeah, I have a list. I mean, I've got.
You have an archive. Nothing's
well, not
lost.
only do I have an archive, I also have. I'll show you something here. NKS hunting.
Yes, right.
And I had something here. For finding minimal models. Yeah, this was another minimal model finding thing. For finding a minimal model for modus ponens logic, for logic with modus ponens instead of substitution, although I think modus ponens is just silly. I mean, we've got substitution is a much cleaner way of thinking about it. Anyway, it was just a thing to look at. Okay, let's look at this. Finite models of this.
Okay.
Okay, what is this? This is 0, 1, 6, 7, etc. So this has, let's write something that just extracts, let's see, if we just say values of this, and then we say map values onto that,
okay.
And then we say array plot.
Okay.
Hash map.
Okay.
I think it's a level 2, but it might be wrong. Yep, there we go.
I see.
Okay, so those are the models.
That's how you do it. Okay.
Right, so these are now.
That's so cool. Wow.
All right, so this one here.
Right. Okay.
Okay.
Ooh,
So
yeah. Okay. Yeah.
Kind of interesting, actually.
Yes, I think so.
And needless to say, no. Let's find them in NKS.
Well,
I think. Is this them? Not quite. Different numbers of truth values. Okay, so I think there must be a thing. What is that? I'm sure I have this somewhere. Okay, that's ordinary Boolean algebra. Forcing operators, we should look at that. Okay, this is enumerating axiom systems and asking which ones allow which models.
Right. Okay. Yeah.
We should probably read this.
What page is that?
Who knows?
It doesn't say at the bottom. Oh, redo.
1150.
Okay. Yeah.
That's another thing that's interesting. Okay. Basic logic, any rules can be applied to any part of any expression. The heck is this? I do not remember. I mean, I remember that thing, but I don't. So notice this comment. In basic logic, any rule can be applied to any part of any expression.
Okay.
That's the statement. That's the business about whether you drill in, whether you apply yourself to the top level operator or not.
Okay. Hmm.
Oh, there's nothing new under the sun. I'm already discussing here variables creation.
No. There's some novelty at play, certainly. And to be honest, I'm glad to say that there are roots several decades old. It makes me feel as though we're building upon some foundations that have a certain legacy. I like that.
Given the axioms of this form, oh, look at that. Look at that. This has variable creation. Right? In that proof, there's variable creation. So these axioms are parameterized in order to allow variable creation.
It's, yeah. I should just go back and read all of chapter 12 again.
Why would just read this section about mathematics?
Well, no, there are some other helpful sections in chapter 12.
You know, it's really kind of annoying that more people haven't read these things in detail because there's an awful lot of stuff here. Okay, forcing of operators by axiom systems.
Yeah, by the way, I mean, what engagement have you had with others regarding these particular topics discussed in chapter 12 on mathematics? How much traction do you think that got?
Don't know. I mean, plenty of people have looked at it. I just
Yeah,
don't think it falls into any. I think the thing is, people have looked at it. People thought it was interesting,
yeah, but that's it.
but it doesn't. What field is it in?
Well, that's why what we're doing now, especially if it's a little more forceful, it can
Yes.
it can
No, I mean,
constitute a vehicle for this, I think.
yeah, right.
That's why this is exciting. Well, that's in part why this is exciting.
Yeah, right. Okay.
Anyway,
Let's read
models.
this thing about forcing of operators because I think it's relevant to this. In a particular set of forms of operators, one can ask whether an axiom system group will allow these but no others. Oh, okay, that's the right. So that's the inverse. That's the reverse mathematics version of model theory. This is a good student project, by the way.
This in particular.
I need to add this to the list of finding operators which are forced, finding forced cases.
Now, not to make things more complicated, but Nick did ask me a couple nights ago if you think that like the summer school or some other school like that may eventually include meta mathematical, I don't know, projects
No
or something
doubt.
like that.
Yes. Well, that's what
Yes.
we're just writing down here. Study forcing of axiom systems from models. Look, this field doesn't exist right now, basically. So let's see if we can create it.
Yeah. Okay, good. There are
Yeah.
so many open questions. And
Yeah.
there's so much, there's even real concrete products that can come out of this.
Yeah, well, I know. I mean, one of the things I want to do is to get the two-way rule stuff working in the language. And once we understand how all of this stuff works. Okay, in any case, let's go back to models again here.
Models.
Okay,
Yeah.
So
Okay.
what's happening here is this idea of a barcode.
Yeah,
Okay.
I like that. Yeah.
So what happens with a barcode is, given a particular model. Okay, so for example, here, let's say groupings right, here's what we can do. Okay, groupings A, B, A, comma, F arrow 2. Okay, now each of these, so let's take a particular form of F, something like this. Okay.
Oh, okay.
So then this, what we want to do here is for any given expression, yeah, now what we want here, and Nick must have something in his code that does this. What we want to do is, given that F has this form, yeah, okay, so what we want to do is we want to make a table with A going from 0 to 1. Well, actually, what it might as well be. No, 0 to 1, unfortunately. B going from 0 to 1.
Okay.
Okay, now, here, we must replace F with the function.
That. Yes.
This function.
Yes, okay, yes.
Where that is hash plus 1, hash 2 plus 1. That's amusing. It didn't need to come out that way. Okay, so let's now do this across all of those.
Ah, yes. Okay.
Why are they all coming out that way? I don't understand this. Why is this wrong? Let's see, F. Well, I mean, I don't understand this. Well, let's just try a different form of F. Oh, what the heck's going on here? What's going on? Wait a minute. Do we need to do this? Okay, something's going wrong because what this should be doing is evaluating something like this, right?
Mm-hmm. Yeah. Mm.
And for specific A and B, like, let's go 0, 1, 0, 0. Okay, so let's look at what this should be. The 0, 1 element is a 0. What the heck are we doing wrong? Okay, so let's do this slash dot F, this thing here. And let us, just for the hell of it, let's echo that.
Mm-hmm.
Well, let's echo these as well. Actually, why don't we just do this? Oh no, what the heck? We can just do that. That's doing the right thing. It's first, it's replacing the Fs and then evaluating. I don't understand why all these expressions are the same. Okay, let's look at the operator for Boolean algebra. 1, 0, so we certainly know that plenty of expressions are not the same if we use that. There are plenty of NAND expressions that are not valid, right?
Okay.
Ah, see, it's giving different results.
Mm-hmm.
Okay, so what this is saying is the model defines equivalences between expressions. Okay.
Okay. Okay. Yes.
And therefore, and then, which means that in the proof graph, this is an alternative to the proof graph, which means in the proof graph, there is an overlay for a given model that connects things equivalent according to that model.
Do people use anything like this
No.
for proofs?
Well, I did for the Boolean algebra thing.
Well, yes, you did.
I have no idea whether anybody else does.
Well, what are its advantages?
Wait a minute. Well, because it's very efficient, it's very fast. You don't have to follow the proof graph. You just go directly. You just say,
Mm-hmm.
there's an overlay for a given model that connects things equivalent in that model. Right. So in other words,
Right, they're equivalent in the model.
Right. So what we're going to do is in this picture, when we get this picture right, okay, what will happen is a bunch of those nodes can be combined according to the model.
And the model tells us.
The model tells us this is equivalent to this, for example, even though the proof graph takes many steps to go there. The model could tell us very quickly what's equivalent to what.
But can it do it faster?
Sure. I mean, yes, models can do it. That's the same.
How do you know it can do it faster?
Well, I mean, you don't know anything, but
I mean, actually finding the models that.
Oh, finding the models is hard. Yes, finding the models is hard.
That's okay. That's what was tripping me up. Or,
right. So, I mean, you can, right. So,
but once you have them,
finding the model
right,
is hard. But once you have a model,
then it's very easy.
So you can either models. I think this is the thing Jonathan has claimed for a while, is that models ? Finding a model is like finding a valid foliation. Maybe. Okay,
Jonathan
so in other words,
conjectured that too.
Yeah, Jonathan claimed that a while ago. I mean, I think, well, in some conversation with Jonathan, there was I don't know whether he claimed it or I claimed it, but he generally said that, yes. So, okay, so then.
Well, couldn't we?
We could do this. We could arrange this picture.
Yeah, we could just do this as we do it with the physics project, and then also make the models and compare them, right?
Well, no, but look, we can take this and we could arrange the nodes in layers according to their model values, so to speak.
Oh, nice.
Right? So in other words, instead of arranging them, and so that is a possible foliation, or not really a foliation, it's a possible observation. It's more like actually more like finding an sort of observer sampling. Okay, but what we can do then, actually, no, this is the wrong way around, because what we want to do is certain nodes here are equivalent. Certain nodes can be moved together based on models.
In a model, yeah, in a model, they're equivalent. Yes.
Right?
Yes.
So, okay. So what does that really mean? What does that mean the model means here? So the model some nodes that are far apart in the proof graph are brought together by the model.
Yes. Does that mean that, let's say you bring them together, what would the branchial graph of that, after these different nodes are brought together, what would that branchial graph
I'm not sure it
express?
means anything because it's yeah, right. I mean, it's look, the model, the bringing things together with a model is kind of an overlay on all of this. It doesn't have the dynamics. It doesn't have the evolution process anymore.
Yeah, it's like a compression of it.
Right, so this picture, okay, so it could be the case that even things outside the entailment cone are model equivalent. The model just doesn't have to respect
Oh
the
man,
speed of light.
that's
Right, because the model, I mean, you know, this whole thing could be just divided into two pieces depending on the values of these tokens under the model.
oh dear. Oh wow.
Okay, but so another way to think about the model
Man.
is, okay, so this is why this forcing business comes in. You can get proof results that are equivalent to model results by adding enough relations. Okay, and that is related to this forcing business.
But like Paul Cohen?
I'm not sure it's the same kind of forcing. Maybe, I think it maybe is the same kind of forcing. I'm not sure. I'm sure I said that somewhere. Let me just see what I said about model theory here.
A model.
For an operating system, such a model can have elements.
Wow.
Axiom system that is incomplete must always allow more than one model. So in other words, if there are infinite proofs, by the way, this is another point here. The what does the presence of infinite paths mean? It's basically computational irreducibility. And
Well, sure. Yeah.
right. Okay, so actually the notion of truth here is basically that find a statement that you think is obviously true, e.g. A equals A. Okay?
Okay.
Now look for all statements that are connected to this. These are the true statements. That's how that works.
Oh, and this can, you can travel between entailment cones to do this. Yes?
Well, I mean, you go up and down. I mean, it doesn't, you're not going up. I mean, connected, it's always got an entailment cone. So true has an entailment cone. It has a future and past entailment cone.
True has an entailment cone.
It's just a statement.
There's an idea.
Right. Now, assuming
That's
that's
interesting. Yeah.
okay. Okay. But I mean, true has an entailment. True as in
That's so important. Oh, but if we haven't really, it hasn't been said that way so far.
I mean, as in has an entailment cone. The reason this is a mess, okay, but if there are other quotes obviously true statements,
Okay.
they could have their own entailment cones.
But that's okay if you have a model, right?
Well, models are a separate issue. This is not that we can deal with models separately, but we can. Okay, so okay, you're right that the model would paint a tautology, right? So given a model, there is a definite representation for A equals A. I'm not sure what it is because the operator doesn't even appear here. Just a second. So, oh no, actually it's really obvious. The A equals A. I think it's a diagonal matrix or something. I'm not sure. There's a definite representation for A equals A. Actually, I'm really confused by something. Oh no, that's right. That's right. What we need to do here. Let's see, just for the hell of it. For this case here, we can just ask, what is that in this case here? Okay, I think that's kind of obvious. Yes, that's obvious. That's what it is. Right, that's the representation for A equals A.
Okay.
Because we got this table, and it's just saying I think that's sort of obviously the representation for A equals A.
Okay.
So then, so all tautologies can be painted by seeing whether their models agree, whether they agree with this, whether they have the same barcode. We should let Nick know where we are.
Yes, right.
So all tautologies can be painted by seeing whether they have the same barcode as A equals A. So all tautologies under the model, which will in general be more tautologies than there really are. Right? There'll be things that agree according to the model but aren't actually tautologies.
Okay.
Right.
Yes.
So there's some cloud in here which Okay, so there's some painting of this, which are the tautologies. And those tautologies they might involve many proof steps. But the model
Yes.
says what's equivalent to true.
Yep,
But
yep.
how does that relate to that's the opposite of a foliation, because a foliation is asking okay, first question is, are there things that are true based on the proof? Wait a minute. Okay, what's the case here? Are there things that are theorems okay, hold on. Are there derivable theorems?
Okay.
Okay, so hold on.
Mhm.
Are there okay, I'm going to copy this picture again, even though it's totally wrong. That's because it's a useful image. Okay, so are there derivable theorems? That are not okay. So assume that from an axiom A,
Hi.
one can hello there. One
Good
can
morning, Nick.
there's some bug which we need to track down. We can okay, assume that from an axiom S, one can derive a theorem T. No, an axiom A rather. One can derive a statement S.
Yeah. Right.
Now, given a model will give a barcode for LHS of A and LHS of S. Okay, so if the fact that S can be derived from A what the heck does it say about these barcodes? What does it say about them?
Okay.
So it says that
Axiom A, theorem S. You get a barcode for both of them. Well, are we considering the situation in which the barcodes are the same?
oh, that's the question. They have to be the same. Okay, let's
Right.
tell Nick about the bug so he can start thinking about that. Okay. Okay.
Yeah.
So what's happening is
By the way, Nick, you're not late or anything. We've just started meeting a few hours ago.
where did we have
Is
that?
it this? Is it the same bug as like on the stream with the Boolean axioms? Talking about that bug.
Yes, but
Yes.
yes, it's related to that bug, but we've got a much simpler case of that bug now. Okay, so this is wrong. Okay, substitution lemmas. See this thing here? This is making statements that just aren't true.
Okay, let me take a look at that.
Okay, do you want me here? Let me send this to you in the chat.
I just screenshotted it. Okay.
Well, it's okay. There you go. Now you don't have to type it. Okay, actually, I'm gonna I'll be back in just a minute here. Yeah, why don't you think about that for a minute? Well, and then
Yes, I need to get some water.
okay, I'll be back in a moment.
Yeah.
Hi, actually, just a minute. I just had an idea. I know we were writing down the stuff about interpretations. Here we go. Okay, so here now. Okay, so there's an important point here. You know, proof structure knits together metamathematical space. Within metamathematical space, what is metamathematical energy? And then metamathematical gravity. And I think the energy, see, we don't really have causal edges here, but somehow the energy
Yes, it's basically proof density.
yeah.
Though I wonder exactly how that relates to what we're describing with models. Now, wait, Stephen, did I miss something? We were discussing truth and model theory, and then you showed Nick this bug, and then I came back from getting my drink of water, and we're talking about the physicalized interpretation again.
Well, we are, yes, because I was looking at it, thinking about it for a second. Then, because I'm trying to understand. Well, I mean, so I think, basically, the expectation is the singularity theorems imply, potentially, if there's enough proof density, the theory will eventually be decidable. But I don't quite know what the signature of decidability is. I assume it's no more new theorems produced. I mean, it's going to be a little trickier than that because we have to have, that's where this equivalencing stuff comes in, because there may trivially new theorems produced even though the thing is decidable. But it might be that it just terminates. So then the question is, okay, so the infinite future of mathematics. There's expansion of the mathematical universe together with a bunch of black holes being formed. It's kind of an image that mathematics is always expanding, but it's leaving behind these decidable blobs. Figured out.
This is getting quite Chaitin-esque. No?
Yeah, it is a little bit. Yeah. I mean, so the picture of the future of mathematics is there are a bunch of burnt out fields, basically. But the future entailment cone, even of the piano axioms. Okay, so future entailment cone of the Peano axioms could still be, well, it is, will still be infinite. But there will be lots of burnt out sort of subcases left behind.
One question I have is, okay, so you can have the entailment, every axiom has an entailment cone. And then let's say you have another axiom that has its own entailment cone. But when we introduce or admit both axioms, and then we generate, say, a graph from that, I mean, is it like the union of their entailment cones? Is it just the entailment cone of both those axioms?
No, it's the union of the entailment cones.
Okay. Yeah. That's fine.
One of the things, okay, sorry. Notion of truth. Okay, here we also have notion of falsity. This is harder to define because A equals A is self-evidently true, but how do you construct something which is self-evidently false?
Well, we have some examples in this buggy code, don't we?
Well, you're claiming that A equals B.
Yes.
Perhaps.
But the other thing about A equals B is that it's like,
that's not really right. It's not really right.
I think, would you say that A equals B is an example of something that shreds the observer? Like its entailment cone, you can't really do anything with it.
I'm not sure.
This is something I've wondered about, which is the relationship between falsity and kind of observer hostile behavior.
Yeah, it's possible that just doesn't make crazy. But let's, okay, Nick, did you have any luck in thinking about this bug?
Yeah.
I
was just thinking about the same bug in co-substitution now. But for substitution, it's a little bit clear how to fix it. And it's fixed already, I think.
Okay, all right, let's try it. What is this in? Two-way multi-replace?
Yeah, right, yeah. Same file.
Okay, so if we run this again, wait a minute, what's happening here? Oh, whoops, why is this? Okay. Okay, so let's now run. Basically, we want to rerun everything.
Yeah. Okay.
Okay, these aren't relevant because they have okay, as soon as we get this, we need to rerun it, right, Nick?
Yeah.
Ah, totally different. Okay. Oh, and in fact, this is now the same as that result there. Is that surprising to you, Nick?
Why those results are
I'm sorry?
different? What's the difference between them?
Oh, one has the Uniquify true and canonicalized true. Is that the default? Uniquify true and canonicalized true?
No, it's basically the same because there's no new variables. The thing I did is Uniquifying after
There are new
making a rule.
variables. Look at this thing. X blank goes to Y blank. There are new variables there.
Then it's
well, let's just check. Okay, so this is canonicalized Uniquify true. And if we have Uniquify false, well, it appears to be the same in this case, although, I mean, that might be a special case that it's the same, but it seems a bit suspicious to me.
well, if you don't, well, if the name of the variables are changed, then it's something different. But it's actually doing the same thing anyway, because it doesn't matter how you name the y, the new variable there. It's just going to be the new variable anyway, and then and they're going to be identified.
Oh, look at that nice thing there. That's good. That's new. Okay, let's try Boolean algebra now. Okay. Okay, now the big whale. Oh, this whale is taking its time. Wow. Did you expect it to take a lot longer than before?
It took quite some time before. It still might take less time than before. We had to wait on the live stream for some time for Mr. Whale to show up. It does look like a whale, actually.
Yes, it does.
With a,
it's probably a Ms. Whale.
sorry?
Never mind.
What did you say?
It's probably a Ms. Whale. Never mind. As opposed to Mr. Whale. There's probably some species which are generically non-binary as well. Anyway, I don't know.
Like bacteria?
No, there are some higher organisms, I think.
Yeah,
So they're ones that well, I think it's trying to render something right now. Whatever it's trying to render is big. Okay, but then from this, we should be able to, I don't know why it's going to be so much bigger.
Well, it took some time before.
Not this long.
Yeah.
I don't know if it's going to make it, but okay. So then Nick's claim is that then these will all be tautologies, correct, Nick? These will all be, sorry, I mean by that, these will all be, for the model in which the dot is a NAND, these will all be tautologies. Is that your claim?
Yeah. If everything is correct, then yeah.
Okay.
I think we've checked for something like that, but adding some sampling, not generating the whole iteration.
So are you saying we could do some sampling?
Yeah.
Yeah, I know
So
we can. I know we can. But okay, so the next thing we're going to need is extracting branch yield graphs from some foliation of these what am I saying? Of these of these token event graphs. Okay, because we want to find out what the distribution, what the layout in space of the mathematical space of the statements is.
Right. Token event graph, the states graph, and also a branch yield graph.
Oh, it has it?
Sorry.
No, are you saying token event graph in its definition has a way of making a branch yield graph?
No, I'm saying these are graphs that we need. These are graphs that we need.
Yes. Yeah. So the compressed. So
Nick. So when we did branch yield graphs, I mean, how difficult would it be to get one from a token event graph?
Well, that's a completely different creature.
That's why I'm asking.
Well, it depends what you want. It's like you want to define your branch of.
well, I think the first thing we could define is to compress out the events.
Well, that's
Okay.
the other way, right? To get basically get a states graph from the token event graph, and then they get a branch yield graph from the states graph, right?
Yes.
So
That's
Nick,
what I would kind of recommend.
would that be easier, Nick?
Oh, it would be easier not to compress it, but to use the function that just uses two-way multi-replace one.
Okay. Wait a minute.
Should
The
be
two-way
just like a global
multi-replace.
multi-replace.
The two-way
Yeah,
multi-replace. No, it does something completely different. We don't want that. That's going to aggregate together a bunch of tokens. We don't want that. We want the individual tokens as nodes. Okay.
What do you mean aggregate them together? They're still gonna each token gonna be each state in the or vertex gonna be just a 1-2 arrow.
Okay. Well, okay, fair enough. So you think that's equivalent to this, but without the events. Is that right?
Right. Yeah.
Okay. Well, if that's the case, then we can use that and then get the branch yield graph from that. But now, does this token event graph, this implies a causal graph separate from the states graph, right?
What do you mean call separate?
What?
What do you mean separate?
Well, I mean, it's a different
I think it's time to kill
like in
this
like in the physics project.
yeah, except this isn't the physics project because this is a
Oh
token.
no,
event.
I'm aware it's not the same project, and that the graphs are somewhat different. But state graphs and causal graphs aren't the same in the physics project.
No, they're not. And they
That's
won't
all
be
I meant, right?
either. Yeah, right.
Yeah.
They weren't the same here either.
You're right.
So this is a little bit disappointing.
Okay.
What's going on here?
Oh.
Go ahead.
Can you try this one? It's like the way we did this checking of the Boolean axioms before with James. Without token and graph, but
Well, what should I do here? Should I kill this, or what should I do?
Yeah, I think it's hopeless. Kill.
Well, but it's in the rendering phase now.
Is it?
Yes.
Oh.
I mean, it's obviously having trouble with the graph layout.
Oh yeah, graph layout. Because we like specified as a layered one, right?
Don't think
And
we
it's
did.
hard
Not
to
here.
layer it.
Not here. For token event graph, I don't know whether token event graph, is it layered? Is token event graph layered?
That I can't have. Well, I'll just check.
This is truly weird, the way that it has these little proboscis off the end. Okay, what do I do to define what's Boolean? So this, I just have to load in here. I have to load. This is, I'm running just a different version, right? So do I need two-way multi-replace in this version, right?
Yes. And yeah, token and graph has like layered graph embedding specified. Maybe that's the main cause of slowdown there.
Okay, let's do this. I hate it when you have variables like G. I'm not going to do G. I'm going to do GGG because otherwise. Okay, so now let's look at these. So this is, oops. So this thing here is what? What on earth is that max leaf count doing?
Oh, that's just for a little bit restriction.
But does it give the correct result?
Well, I
Yeah,
suppose it
it's just
gives
less.
part of it. It gives part
Just
of it.
less result.
It's like sampling, right?
Yeah, okay, but this is also going crazy. Maybe your machine is much faster than mine.
Maybe I just
There you go.
haven't rendered it. I just did it without rendering.
Okay, so now if I say vertex list of this,
Right.
Okay.
so here I should be getting true statements.
True
of both.
statements. Well, let's want to do the test.
Yeah.
Yeah.
So what is this now?
Well, this is kind of manual test without all those tautology and Boolean functions. Just generate all combinations, tuples of true and false,
Yeah, okay.
and substitute them.
Why is this running? What the heck? Why is this now spinning? Oh, I see. If I go outside the window, it spins. It's like I step off the island. I've deep ocean. I don't think that one is going to survive. Oh. Well, they're all true.
Ta-da.
Yeah.
Okay, so I want to see some of those theorems. So we had previously, we had a bunch of theorems over here. I've got to kill this, unfortunately. Drat. Is there any way to limit the number of things generated here? I don't know how to kill this even. I don't know. That's not going to work. I'm going to have to just kill it completely.
Yeah, I don't have any limitations for the substitution lemma. So you have to like, I
You
don't
don't
know,
have-
sample
Yeah, okay.
inside the rule.
I see. Okay. All right. Okay. But now, so one of the issues there. Okay. Actually, if I just open this. Do we think this is correct? Yes, that's presumably correct because it doesn't have any of those variable. It never has to create a variable, right? Do you think that's correct?
You run it.
What's that?
You can always rerun it and see whether it's the same one.
Yeah, but now does this doesn't have the canonicalize and so on things in it?
Yeah.
Should I put those in here?
Yeah, why not?
Okay. Encouraging. Okay, now this one. Okay. And that gives the same thing as well. Now this here, okay, so here I run this. And do I need to put in, I can put in the Uniquify and canonicalize here, right?
Yeah.
And I put that in right there.
In substitution. Yes. Right. No, not. Yeah. Okay.
Okay, that's encouraging. Yeah, I don't think it's going to make a difference for these. And you say it doesn't for that for some reason, which I don't fully understand. Okay, so if I do this, okay, that's X goes to Y and X. Okay, all right, so given these, now we're going to, bit of a drum roll. Okay, so this stuff, if we look at this here, this is probably still the same. Okay. The following is presumably wrong. Okay, so this is a claim here. That's an important claim, that pure substitution without co-substitution is enough because these axioms have just one variable on each side, on one side.
Right.
Okay, so here, Okay, this is full Boolean algebra. Oops. Well, we believe this is going to work. We should check it, but we believe it's going to work. So we can delete this stuff here. Actually, let's just check this, okay? So this is Boolean algebra here. Oh, this is what we want to do. And then we want to do vertex list of that. Oh, that's interesting. Canonicalize false. Let's make that canonicalize true, which we still believe will work. Okay. Okay, so those claim to be statements of Boolean algebra. Ta-da!
Aha, all right.
Ta-da! Da-da-da. Okay, great. Excellent.
Good.
Okay, now let's go to our mathematics search, and then I want to go to the model theory case. Well, okay, then I want to get branchial graphs from this. So you say, okay, so you say this thing here, okay, this is the way to get, okay, here we get, this is probably all nonsense, so let's just remove it. So one question is, will this give all the true statements of Boolean algebra? Will this here, will pure substitution give all true statements?
How would you test that? Can you test it?
Sure. We just see what when we've got an enumeration of the true statements of Boolean algebra, we just go, will pure give all true statements of Boolean algebra? We've got an enumeration where we just enumerated all possible expressions. Okay, can you make a note? We're going to go back and do this, okay?
Yes. But my question is, how should I say this? This is one generation, one iteration. If we do two, there'll be more. Are you supposing that at some point it ends?
No.
Because otherwise it's infinite. And
No,
that's
no. We won't be able to prove it this way, but we will be able to.
that's why I'm asking, right? Because
Right.
there are an infinite number of statements.
Yeah.
Yeah,
But I
okay.
mean, it might be
Yeah, just making
provable
sure.
that pure substitution is sufficient.
Okay. It's a great question.
I don't know whether there's this thing called this is post-lineal theorem, which I vaguely think is related to this. I don't know.
Wait. I've never heard of that.
Lineal. What is this? We show a Hilbert-style calculus containing only the axiom A goes to B goes to A is undecidable. When is this from?
Where did you find that? Did someone?
I just typed it in for.
Oh, I see.
Types 2017. I'm surprised by this. I don't even know what this is, but. Well, somebody finding minimal.
This is, how close does this get to rheology?
Well, this one is, well, it's
Whoa.
pretty rulal to me.
Yeah, that's right. That's what I'm asking.
Yeah, I think you should make a note of these characters.
Yeah, yeah. Okay. Here, I'll take a little. You can email it to me.
No, I was going to give you I was going to put it in chat.
Just as good. Yeah. Message from Steven.
Okay. I don't know what this is such a complicated area. Okay, in any case, maybe Matthew Sudzik or Roman Maida would know the answer to this, whether this is let's formulate this and send it to Matthew. Okay. Let me just make a note. It might be related to the cut elimination business. I'm not sure. I don't know. Okay. All right. So now, okay. So this is okay. By the way, here. Okay. In each case, we can get the pure multi-way states graph like this. So now we would take this here. And we would say, what's that last doing there?
Because list of graphs, like 2 iterations.
Oh, I see. I want to see them all. I don't want any of those maxes there. Okay, so now here, instead of this, I just want this rule here. Is that enough? Is that okay?
In my list. Yeah.
Okay. Okay, lovely. So this here should be, if I go to one step for this, it should give exactly that same thing. But it doesn't. Okay, so why is this different? X goes to YYX. Okay, why is this different?
Because of Uniquify.
So can I Uniquify here?
Yeah, the same options.
And the deduplicate true is what I want, yes?
Well, I guess, yeah.
Okay, and we're not showing those double edges there. So that's AB. A goes to BCA. Yeah, it's looking good. Yeah, it looks good.
Good.
Oh, and there's our tautology.
Nice.
This one derives a tautology.
Great. Great.
Now, I don't quite understand one thing, which is these are two-way rules. Why is there no back channel here? Why does it not go backwards?
Maybe in the second iteration, it can go backwards. It's just one step, right?
I see what you're saying. Okay. So let's see whether we can get to the third step here.
Are you sure?
What's that?
That's too much. You combine all pairs of those vertices together on the last graph there.
Okay, I admit that's too much. Stop.
Oh,
We just crashed. Splatteroo.
by the way, Stephen, can anything be done in the future to permit, or just to make it easier to do this with more complicated graphs? Basically, can this be overcome at some point?
Which issue?
Just the fact that when we try and do like 3 iterations on many of these, the kernel dies.
I don't know.
we
I
can't
mean,
compute it.
I don't think it's a question of where there's a problem. Is it running out of memory? Is it? I don't know.
Yeah, I don't know. Well, I thought maybe you would know.
I don't know because I don't really know what's happening here. I mean, I think
Many ways can happen.
what's that?
Many ways can happen. I even like have filed a bug recently that crashes trees just by trying to extract
Oh
the
yeah,
position from
yeah, I
them.
remember that bug.
Okay, but so here we've got a bunch of relations here. This is beautiful. This is really nice. So, and notice that true is in the middle there.
Which is nice.
Right.
This is good. These are good examples.
They are. Yes, they are. Decent
Yeah.
examples. Now, okay, so let's go looking at our releological results, and then I want to look at the branch hill graph. So this should be easy to derive a branch hill graph from. Is that a true statement?
Yeah.
Do you have code that does that?
Well, it's how it was before. It just gets all the vertices there and their ancestral edges, and that's it.
Okay, fine. But do you have code that does that right now? So we could just look at the
Yeah,
branch hill graph?
it's already should be loaded. So lowercase branch hill graph for any graph. Just
Okay.
give it any graph.
That's beautiful. That's just beautiful. That's completely magnificent. There's true over there. This is really magnificent. Okay. So well, there's a piece of metamathematics all laid out. That's quite something, because this is where we're going to see the non-trivial homotopy. This could have an event horizon in it or something. If it, well, we won't see that. We might see something in this branch hill graph. Okay, so let's take this. I've got this here. I just want to try up here. That's a token event graph for that. So now what we want to do is go here. Okay, so here I want to try Is that graph there? Oh, that went to step 4 steps. What the heck is that? I don't understand this. What? Oh, I see. There are only 3 nodes.
It's basically 2 because you don't canonicalize the first one. So it kind of goes into this dumbbell there, and it goes back and forth.
Okay, so now let's try. Okay, so now I want to try the case. This is really nice, by the way. This is really, really nice what this is all doing. It's quite magnificent, actually.
It's nice to see all this come together after all these weeks of working on all these separate pieces.
Yeah. Oh, well, this one is too big. Oh, there we go.
Okay, great.
Okay, so this is, okay, so there are the 2 initial points. There are the 2 initial axioms. And then these are derivable statements. Does that end there? If we run it for another step, it's not going to generate any more, I think. I think this ends there.
So it's decidable.
So it's
an
decidable.
example. All right.
This is the universe ends.
Well, if you want a nice looking graph for decidability.
Right. In this
That's
case,
that.
the universe ends. Okay, and we can get a proof in here. We have in general many proofs of some statement like this. Whoops, the edges here are labeled. So the statement A, this statement here has some number of proofs.
Mm-hmm.
Which may be distinct, or they may be. The question is there a topological obstruction getting from one to the other? Oh, we were going to make a branch hill graph from this. Nick, you really need to get this branch hill graph function into the function repository. Oh gosh.
This is just a branch of hypergraph and the colors. I don't think it should be a different function.
But what level is this at? Is this? But this isn't a hypergraph. This is just a graph.
Well, I mean, the function, it calls the hypergraph with argument 1. So it just considers one level of ancestry.
Okay. Well, this is the map of where these expressions lie.
Mm-hmm.
At what level did it slice this to get this graph?
Well, it's not slicing. It takes all the vertices there. So it assumes it's the last layer of the whole graph, not in a way.
I think we need to understand that a little better. Because there should be a series of time steps here. You see what I'm saying?
Right.
If that's a layered graph, there should be.
You can just like remove all the vertices that in the previous graph.
Actually, why don't we just map the branchial graph over these here? Right?
Yeah, it's just going to be increasing hypergraph, increasing branchial graph. But if you want like the last slice, then you probably need like something to take differences of those graphs.
Yes, I agree. If you could make that, that would be great.
Or just fold something like vertex delete.
Really? Like what?
Yeah, why not?
Yeah, it'll be something like that. I agree, but I don't know what it is exactly. We should figure that out. Okay, but let's not get derailed on this right now. I'm just admiring these graphs. So what we should see is in this mathematical space, the entailment cone has some shadow on each branchial slice.
Entailment cone has a shadow on each branchial slice.
Right, it gets bigger. You start from this, well, that one, it'll just be the whole branchial graph. But if we start an entailment cone from here, that would be small on one branch and we'll get on one slice and it would get progressively bigger on later slices.
Nice. Yes. Okay.
Okay, so then
Yes.
the joint entailment cones. Okay, when we add more relations here, could we ever get inconsistency? Could we ever have two relations which can't simultaneously be true? I don't think we can. Okay. Let's go back now to our little releological study, wherever that was. What the heck is that? I don't know what the heck that means. I'm not sure I've ever seen that before.
Really want to try it again?
No, it worked before. It worked fine before. Okay, so now this thing 24. Where are we doing the releological stuff? 25. Okay, this 25. And this is where we're enumerating possible axiom systems, and we got bitten on those bugs.
Ah, yes, right. But now we can address it. Yeah, let's see what these look like now.
If they come back. Oh,
Okay.
so interestingly, they're basically the same. So this is AB dot B goes to A, and A dot B dot A. Well, let's see whether these are actually the same. They sure look like the same graph. I mean, those may be equivalent. Okay, so there are those relations. Why isn't that tooltipping?
Have we had tooltipping for the token event
No.
drives? No.
Okay.
Well, we
So if I
have
say
like
true here,
have token rendering function. I think if you just say tooltip there or something like that.
okay, notice that true is showing up there.
Very nice. Right.
It's going to
Although-
always be a true if you have one variable on one side. If you consider this as true.
Yeah, okay, fair enough. What do you mean? If it, no, but that variable equals the variable is true.
Yeah,
Okay.
it's the most trivial kind of reflection I can do. Yeah.
Okay, now this is going to be the results. Okay, so these are now, we really need these trees. We need to figure out how to label these with A's and B's, or actually with different colors.
Different
For
colors.
the, yeah. So can we put that on the list, please, and let's figure that out.
Yes. Unless Nick has an immediate solution.
So what happens here exactly? The token.
So what this is doing is it's taking the expressions and drawing them as trees. This find tree thing. It's not very good.
And you want like the left child color.
No,
and
no,
right-
no, 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 no.
Like
We just want the
A
leaves.
to have a different color. B to
I want
have
the
a different
leaves to have
color.
different colors, and if we end up with different operators here, I want those to have different colors. I mean, it's just some setting for tree.
Oh, get it.
Okay, this is the A dot B equals A axiom system. After one step, let's check it here. Okay, let's do it after two steps, see what it does. That's quite lovely.
Nice, nice.
Okay, so these are the theorems generated from that axiom system. Okay, so what will happen with these theorems is every theorem here, for any given model, there will be a number associated with these. And that number better agree for any model, right? So whatever the number, whatever the, or the, sorry, the matrix for this better agree with the matrix for this.
Okay.
Okay, but there may be also ones where the matrix for some other tree would tell you there's a theorem, but it isn't a theorem that's derivable by the proofs.
One more time. What was that?
Okay, so these things here, okay, so let's go back. Where do we have the model theory stuff?
Is it at the bottom of 25?
That's here.
Yes. Okay. Maybe we can get rid of this relic now.
No, I want to keep it. It's a useful guide to something. Okay, so now let's say enumerating trees, enumerating expressions with a values of expressions for a particular model. Okay, so now what we want to do is, given a particular model, like this model here,
Did you use find finite models?
Yes.
We've been using find finite models. Yes.
Yes, it's worked beautifully.
I've learned, yeah,
There it
I've
is.
learned quite a bit about this today. This is really fascinating. Yeah.
Yeah, it's an important function, Nick. It's very useful. And
Nick,
even-
Nick, how many functions have you produced since you joined Wolfram Research?
well, this one was even produced long before, I think.
Well,
Anyway,
okay.
it's Nick is prolific.
Prolific, yeah, right. Prolific.
Okay.
ties up, yeah.
Okay. All right. So this Nick, if you have a better way to do this, I'd like to know it. So I've got, given a particular model. Okay, so these are particular, okay, let's do this. I need to make an expression graph of that. Okay, there we go. That's what I wanted to show. Okay, so there's the model.
Nice.
And this, so what this is showing is these trees are equal according to the model. Okay, but they may not be equal in the proof theoretic sense.
So what's the usefulness of identifying equivalents within the model if they're not necessarily?
I don't know. I
proof
don't know what the
equivalent?
interpretation. The question is, what's
Right,
the physical
exactly.
interpretation of the model? Right. So, you know, what's the analog of this in physics? I suspect, you know, Jonathan suspected that it's basically building foliations. So this is for a size 2 model. These are the values of that tree. Is there a better way to get that, Nick? The values of a given expression. Because that's very similar to your find finite models thing, except it's the other way around. It's the evaluate something in a model.
I'm not sure.
It might be useful to have that function. Evaluate in model. I mean, it's trivial. It's just this, but it would be nice to have it so it's dealing with all the variables correctly and so on.
Not really. Where do you even use A and B inside the table?
It's used because of this.
Oh yeah.
It's a little bit weird and hokey because if those are pattern variables, the ordering in the model is a bit unclear, right? I mean, those pattern variables could change their names. Oh, no, I'm sorry, that's not right. That's not right, because the left-hand side and right-hand side have to agree. Okay, so the question then is, okay, so this is a decent example of where there are equivalences generated by the model that are different. So now the question would be, given those trees, given those expressions, are those first three expressions equal in a particular axiom system?
Oh.
No, in an axiom system. In other words, they're proof theoretically equal.
Okay.
For what?
For what axiom system, or within what axiom system? Within the entailment cone of what axiom system are they equal?
Right. So one thing we could do is turn those two things into the equivalent, the equality of those two things could become an axiom system. And then the question, does it imply the third one? Now, how do we get, now we want to get the, where is it? One of these things. So this is not wrong anymore. This is right now. So now we want to take this. What are we doing here? We just want to say, oh no, instead of that, we want this. Like, okay, so the question is it going to be equal to number 3 there?
Okay.
Which is A dot B dot A. And so the question is there an equality? A dot B dot A, this thing here. How do we figure this out? Whether that's a true statement, whether we can proof theoretically establish that true statement. I guess what we do here is we run this. We can run this again. Let's run this for the with this guy here.
Right. And then try and find a path.
Yeah, well,
Yeah.
it's not a path, it's just a
Hmm?
here.
Oh,
It's not
just
paths
right.
anymore.
It's just a node.
Yeah, it'll just be a node. Okay, all right, so now we say vertex list of last of that. And then what we want to know is does A dot B, okay, let's get rid of the, how do we get rid of the whatchamajigs, the patterns? What's the thing for doing that?
P underscore capital P pattern goes to
First P.
first P.
Okay, so now what we want to do is we want to say position n% of this thing. Splatteroo. Doesn't occur. Okay, so therefore the model is establishing a relation that cannot be derived proof theoretically.
Oh my goodness. Right. What does it mean though?
Well, it means that the model is equivalencing, is pulling in
Yes, right. Okay.
equivalences, which are simply not.
Within the same entailment cone, right?
Yeah, but they're not only not within the same entailment cone, yes, they're not in the same entailment cone, they're just free floating in the gas.
Oh man.
Right, it's free floating because that relation between this and something else just never occurs with that axiom system.
Spooky.
Well, it's that models are a way of a model is a superluminal, it's Bohmian mechanics in some sense. Okay, it's trying to find, yeah, I mean, it's reaching out beyond where, I mean, this makes sense to me. This thing is, I mean, I'm still trying to understand a little bit what this means in physics. This is defining, let's see, it's like a hash code. Yeah, two things which are model unequal.
Mm-hmm.
Models are like hash model values. I don't know what a model value is called, actually. Model values are like hash codes. If they are unequal, then the statements can't follow from each other. Right? But if they're equal, that might just be a quotes coincidence and have nothing to do with the proof, nothing to do with getting from one to the other by a proof.
A coincidence.
No, like a hash code. I mean, it might be a hash collision.
Okay. Yes, I see.
Can there be like another entailment that can get us there, like co-substitution?
Yes. Wait a minute. If they're unequal, they cannot get from one to the other. Co-substitution, substitution, anything else. Right? But it could be the case that if they're equal, one form of proof. Okay. If the model codes are equal, one form of proof, e.g. substitution, might not connect them, but another, e.g. co-substitution, might do it. Okay, I got a question. If we start, we haven't started looking at co-substitution, but we can perfectly well do that in a token event graph, right?
Yeah.
We can do co-substitution in a token event graph, yes?
Yeah, because I have a co-substitution lemmas function.
Right.
Similar to the substitution lemmas.
Right. So the one thing we need to do here is to make the final connection with find equational proof. Although I think that's going to be fairly straightforward. I think we just have to introduce the co-substitution lemmas. We then have a token event graph. It is then, it's not quite a path in the well, it is a path. It's a tree in the token event graph. It's a tree that leads to tautology in the token event graph. Is the that makes sense?
Yeah.
Now, okay, so this was an enumeration of possible axiom systems, and then what we want to do is for each axiom system, we want to build probably, do we want to build the token event graph, or do we want to build the I think we probably want to just build this thing. Let's just build this thing. Okay, so for each Okay, so let's see, what do we do here? So that's the most trivial case, and that's, I think, the case we already did. Oh God, what's this doing? No, help. Okay, let's just do this for 2 steps. Okay, great. That's the case we already did. Okay. Now here, we have another set of axioms. Why are these all the same? Why on earth are these all the same? Nick, any thoughts on that subject?
Not really. Do you use them there properly? Like two-way multi. Okay.
This is very weird that they're all the same. And in fact, if we just do how do we do this? We could say group by.
It may be the same because it's like always the same set of positions when you can apply the rule.
Okay. All right. Well, let's try a different thing then. Okay. Let's do. Well, this one here is much longer. Do you think this is always going to be the same too?
Oh, it's harder to say. But the fact that there is like variable only kind of appears in the same position.
Let's try this case here where this, instead of AB, it's just A there. Okay. Let me just make this be group by first, and then let's say map over these. How do we do this? We just say labeled first hash sub 11, comma, and then we want to say for each of those, it's last slash at hash. Oh, come on, what happened here? Wait a minute. Wait a minute, group by, what does group by do?
Makes an association.
Wait a second. What do I want
With
here? I want to make this. I want to collect these.
by applying the function.
I want to collect all the ones that have the same first element here. Am I totally confused? Let me just see. What does group by do? I thought I'd used group by 1,000,000 times. Oh, I think I need to just do values here. What is going on? What's going on? Maybe these aren't the same. But why are these? Do you see what I'm saying? Maybe these aren't the same. That's why they're not grouping. Okay, they might not be the same. All right, let's try this then. Well, no, I see what you're saying. That was ABAA. So I'm just trying to select. What happens? I just do AAA. Okay. Okay, that may be kind of trivial. Those are those rules. Okay, so now if we say overbar arrow 1, is this going to do something totally trivial? Oh, there aren't any. That's crazy. Wait a minute, why aren't there any? Groupings, that's a unary operator. Well, okay, I guess there aren't any. So then we have I'm just looking for simple cases here. I mean, I've got center dot arrow 2 here. Now this will be quite a lot of stuff. And we should have done this in parallel. Let me do this. Ah, my gosh, I just killed it just as it was about to output. Well, let's see. Sorry. Okay, I am again confuzzled. Are they identical? Okay, they all seem to be identical.
But they have different vertices, right?
Yes, they do. But their structure is identical. Why? They have the same operators. Go ahead.
Because as I said, there's like only the same set of positions when the rule can apply. You have an A on the right hand side, and there's always two positions that there's A in the left hand side.
Okay. Okay, so I'm not sure
It's
quite
not
what we're trying to.
it's not the same places, but in the same number of places. I guess A can move around.
I don't know why that makes these graphs all the same.
Because like if just the same number of positions, then it's gonna have the same number of outputs, and then again, it's gonna be the same number of A's on the outputs, and then it's again the same multiplicity and connections.
So if I take this, put it in here, let's try living dangerously and going to 3 steps.
Okay.
And basically what this is saying is this is a self-generating thing. That makes use of existing lemmas. Oh, we've seen one like that before.
Mhm. Many of them have that kind of structure to them. It's actually slightly different than the one we saw before.
Yeah, it is.
Before this project, have you ever seen graphs that look like this?
A little bit.
Maybe in the Combinator book or the Euclid post. Whoa.
And that's not very useful.
That looks like
But we can now take this thing and make a branch hill graph from it, right?
why not?
Maybe. You think it's just gonna make a big mess like this?
Yeah,
A little ball.
and it also is not very efficient. So
Usually
you might
when
never-
branch hill graphs take a long time to render, they end up just looking like little
Blob rays.
like little coronaviruses. Yeah.
Okay, let's look at this one here.
it also may take a long time to actually compute them. So
Okay, that's
Ah,
already
yeah, okay,
fairly
good.
complicated. Okay, so once again, one of the questions here is, given this branch hill graph, for example, are there several detailed axioms which we would say these are all the such and such theorem?
Say that again.
Okay, even in Boolean algebra,
Yeah.
there are arguably, okay, are there clusters of nodes here that would be named the same theorem? In other words, they have some kind of difference, but you would still, as a practical matter in mathematics, call them the same. I don't know. I mean, you clearly, if you rearrange the structure of the expression, you clearly would name it the same, or okay, all right. So this is this. Okay, could you remind me what else we need? So we need the co-substitution stuff. What else do we say we needed?
To color those trees.
Yeah, we need the coloring stuff for this.
Let me look at the notes
And we need a bunch of detailed things, just detailed ways to render things and so on.
We need to wow. Let's see. Okay.
We need to answer that question about pure substitution.
That's what I was going to say. Yeah, right. Understanding.
Okay,
if we can generate variables without co-substitution, and then there's also looking at multi-way combinator.
Oh yeah, right.
We haven't done.
Then there's the okay.
And there's metamath.
Right. Okay. Let's. Okay, so we've got two branches here. We've got co-substitution. We're going to have a quick look at co-substitution, maybe.
Oh, and there's also find equational proof.
All right. Okay. Yeah. Can you make a list of those and send them out? So, because we want
just
the most,
like put them on the chat, or
no, and send them an email because we're not going to get to them all tonight.
Yeah. Okay. That's fine.
So we want the most trivial case where we can pick out find equational proof from the token event graph. Okay, but that's going to require co-substitution anyway, I think. All right, so let's go back here. And okay, so now let's make a MetaMathematics 26 where we're also doing co-substitution. Okay, now so this is now about co-substitution. So we had that very nice example before where we could see a minimal case of co-substitution. Where was that example?
Yes. Right. Oh gosh, my memory. Is that just like within this call that we had that?
No.
Was it in the live stream?
Don't remember.
Yeah.
It's in 22.
It is.
Okay, this is the understandable version of co-substitution. Was that the most understandable version? I think we have an even more understandable version.
Okay. I think that was it.
No.
Was this the most understandable version? I thought we had something even more straightforward, in which we just said, Nick, what did we have? We had A goes to B, X goes to Y or something.
No, you should have at least one variable repeating in order to see an effect. On the left.
What about A goes to? What's that?
Yeah, A equals to 8. I don't know. Maybe it's.
Sort of, but let's try A goes to AA.
Yeah.
Yes, there's an effect there. Right there we see it. X, Y, X. Gosh, I don't understand this. Go ahead. What were you going to say?
It's a pretty weird rule. Again, it's like any variable goes to any variable.
Okay, but do you think this one is the less trivial one?
Well, at least the rule is like a proper one.
Okay, but
in-
so
in-
walk
it's
me
a nice
through what we can
example.
get here. What we get here is yxb. All right, so let's look then. So this is the co-substitution case here of that first rule. To be compared with the substitution case. By the way, don't we need the Uniquify here again?
maybe it's a little bit trickier with the co-substitution. So I'm not sure about how it actually interacts with unification. To actually do
Was it Uniquify?
right. The same.
Oh gosh. Look. I'm trying to abort. So do you think you've managed to get this right, the unification yet? We crashed.
Or what I did. It depends. Oh,
Are you changing something?
not yet. I'm gonna leave it for now.
Okay, but you think it's probably not right.
I can say maybe it's right in some sense. Right, you just have to understand what is actually unifying. You unify in the co-substitution lemmas. Like in the case of substitution lemmas, you unify the right-hand side. All right.
Yeah, here it's more complicated.
Here I actually unify the left-hand side. Something like that.
Okay, well, this is the contrast between the substitution lemma and the co-substitution lemmas. This is a substitution lemma. Says AB goes to AB and AB goes to BA. Whereas here, there's AB goes to BA. I wonder whether it matters that we unified. Let's try it and see whether it makes any difference. It did not in that case, which is a good sign. So there's AB goes to BA, AB goes to AB, and then there's also these things here. Right? It's a richer case. I don't understand why this is a one-way arrow here. Why are these one-way arrows? Whereas this one is a two-way arrow without unification.
Because it's one step there. If you add another one, maybe you'll get another arrow in opposite direction.
Indeed, we do. Okay, all right, fine. And so this one here, we probably get another arrow as well. Okay, so this is a fairly nice example of what happens with co-substitution. Now the question is, if we use co-substitution, so basically, if we grew this another, we did co-substitution here, and let's do vertex labels, no vertex labels. Oh, okay. All right. So this is co-substitution is now. Is there a way of getting tooltip vertex labels here?
Oh, just
Look at this.
vertex labels placed name tooltip. I guess.
That's interesting.
So this basically, unlike
That's interesting.
pure substitution, which doesn't really get anywhere.
Oh yes, you get places with co-substitution.
Yeah.
Oh yes.
Okay.
And in the chat, I send you how to make our tooltips.
Great.
Those.
The quotes were too smart for us all. Now, we can also do this with your two-way whatever thing, which should give the same result, shouldn't it?
Right. Yes.
Let's check that, and then we can get a branch-all graph from
What's
that.
the two-way whatever thing?
This-
Oh, two-way multiple place graphless. Yeah, that's quite a mouthful. Yeah, okay.
Well, you the only difference that you have to like make it not accumulative, right? With the rule selection.
Why?
Because there you apply the same rule to the co-substitution, right?
I'm confused. What are you saying? No, I'm not. No. This is the same. Oh, you're right. Right. This is non-accumulative. Okay, but if we wanted to do them accumulative, okay, now this is the accumulative case.
Nice, nice.
Okay, which we can also do with a token event graph.
Right.
Which you're
It's
going to show me.
naturally
how to do.
accumulative.
What's that?
Which is naturally accumulative.
Yes. Okay, there's the token event graph. And in this case, what we're doing is we're using just that rule, right?
Yeah.
Okay, that's substitution lemmas. That's substitution only. Then let's do co-substitution.
Mhm.
Let's do 2 steps of substitution here. Not very exciting. 2 steps of co-substitution.
Can we? Mm,
Let's find out.
come on.
I think it might work. I think the problem is probably the token event graph doing layered digraph embedding, which we probably don't even want.
If you specify a layout, maybe it's just gonna override it.
Yeah. Oh, I was just about to kill it and it came back.
Okay. Interesting.
Okay, so that's now the co-substitution. If it would only stop spinning. That's what we get with co-substitution. And now we can also do the thing without the events. It's unbelievably complicated. I mean, this is unbelievably complicated already. And we'll find out what trees correspond to those relations.
Yes.
And they'll get very complicated, I'm sure.
What about the models?
Well, I mean, the models for this, we should look at the models for the X, Y, YX thing. Yeah, we should look at that. Okay, but there are two directions here. What the heck happened there? Why is this going crazy?
Too many edges.
Possibly, but that doesn't usually kill off a notebook like this. Anyway, so okay, we need to talk about combinators for a second, and we need to talk about MetaMath for a second. Then I need to go to sleep.
Oh wow, wow! Time flies. Okay, multi-way combinator. Oh,
right,
by the way,
yeah.
There's some problem that I was reminded of during the live stream. It's not, I don't think it's multi-way combinators, some multi-way function. It needs to basically be de-stringified.
Yeah, they all do. Every multi-way function needs to be de-stringified, okay?
Nick,
and what we need to do is
Nick, do you know how to do that?
It requires a rewrite of the rather horrendous code that's the multi-way system code.
Oh boy.
Okay, and I think what we need to do, it's part of the multi-computation design, and we need to just get that design right and then just re-implement everything. Okay, now.
Well, what's the preferred timeline for that?
I don't know. I mean, we're working. We need to have another meeting about the multi-way computation stuff.
Okay, I see. Okay.
Okay, so now this is substitution lemmas to false. Let's just do the first case here. It's just substitution lemmas only. That's utterly boring. Let's go 2 steps. Okay, that's substitution lemmas only. Now let's go only 1 step because I'm nervous about what's going to happen. Co-substitution lemmas are true, and substitution lemmas are false. Okay, let's go to 2 steps.
Okay.
Well, it's going to be this thing again, because that's 1 step. And what we see there is there's multiple edges to that thing, but that's going to be a repeat of that big creature. But once we have that without events, but when we have that, we can make a branch-all graph of it.
It's even gonna have more edges because token event graph kind of compresses them. No, it compresses events. even essentially compress the edges. But when you have, if you remove the events, you just have to like multiply all your inputs with your outputs.
Yeah, right.
So it's going to be like more edges.
Yeah, well, let's give up. Okay, we can separately try and get those. But it's crazy that it's absolutely freaking crazy. Okay, so in this case here, we can take line 18. And then what do we want to do with these? We could show them as trees. Where's our tree maker? I think that's enough, right? We just need the tree maker on let's just do that for a few of them. Oh, for goodness sake. How do we make these tiny? I just do show? No, I don't think so. Let's find tree. That's better. $796 relations. Here we come. How big did they get? My God. You know, arguably, it's things like this that are the reason why nobody's done this project before. Because to get intuition about what's going on, you have to do these experiments, and these experiments are totally trivial.
I'm not sure that's the barrier.
Possibly.
Hey, okay, look at that.
Okay, so these will have different labeling. These are fairly non-trivial relations, which we're getting just from, I mean, it's just freaking bizarre. They're just commutativity gives all this non-trivial stuff.
Complexity from simple rules.
Well, I know. I mean, but basically the reason is because substitution is a treeifying thing. That's why this is non-trivial. I mean, some of this stuff is pretty ornate for just, how many steps was this? It was two steps. I'm sure if we can make this, we can compress this a bit by making isomorphic things. Okay, so we need to make an example of find equational proof. So any thought that can go into that will be very helpful. just an example of one of these things. Maybe with this can we see how to do that immediately based on this? You know, is there a path through that existing token event graph there? There should be. That will be the find equational proof path, which will take the original axiom. Okay, what we're going to do is we're going to have the original axiom and, you know, again, the find equational proof version of this is I wonder if this is actually, I wonder if I do union of this, whether it will do anything interesting. Not much. Yeah, I mean, this has to have, it needs graph isomorphism. Okay. Anyway, okay, find equational proof. We need to figure out how that works. Then, metamath. We were just starting to look at metamath. Maybe we can just pull that up again. Okay. What are we going to learn from this? Nick, how should we think about this relative to what we've been doing just now?
Oh, no, the easiest thing is like you can make functions out of any proof in MetaMath, and find equational proof objects also have proof functions, and they're essentially kind of doing the same thing.
Okay, so a proof function is just
It's
saying
different.
apply these substitutions or co-substitutions, and then just apply them, and the result is true in the end, right?
Right. It's just in MetaMath there is no the result is not the true, but in your actual theorem statement.
Right. Okay. So it's building up the theorem statement as opposed to find equational proof, which is burning down to true.
Yeah.
Right. Good. That's what we're looking for.
Okay. Okay. All right. So in find equational proof, one burns down to true. In MetaMath, one builds up to the theorem one wants.
Yeah. If you just reverse the tree, turn it upside down, then it's the same.
No, that's lemma one is being derived from these things here. Is that correct?
Yeah. Not
So
derived. It's an argument to it, because the lemma has arguments. So basically, you can use it, this lemma, inside your other proofs, just providing anything for these 4 variables.
I see. Okay. Okay. Fine. How the heck does that relate to what we've just been doing? I don't see how that relates. I mean, because what we wanted to do here.
That's kind of similar. If you like reverse this graph, you have these merges of some kind of expressions coming into a node, and you can look at it like an event.
Yeah, I know that, but why? Okay, so this is like a function taking arguments. But now, how does that relate to anything we've done? Because in the end, our theorems are exactly things that take arguments.
Right, but also any event in the token event graph is like it's a lemma that takes arguments, our theorems, right?
Yeah, I agree.
So MetaMath doesn't work with
Wait. But the lemma. Right, our events in the token event graph are pure substitution or co-substitution.
Yeah.
Yeah.
Whereas here, these events are something different. By the way, do you understand enough about lean to know whether it works the same way as this?
Well, lean is much more complicated.
Oh God.
There's too much stuff going on. Right, yeah.
Should we ask some people who understand lean better how it relates? When you say there's too much stuff going on, what do you mean? I mean, in terms of its workflow, what is the workflow?
Well, there's like type theory, there's like type inference going on, right?
Yeah.
It's not as simple as doing substitutions.
No, I understand, but the question is whether the workflow. Okay, so this.
So I guess if you look at the
existing
lean function,
yeah.
If you look at the lean function as just doing substitution, right? Because lean is a pure functional language. So just as applying any function or any proof is just like a pure function, or the same tree as in MetaMath in a way.
Okay.
So maybe in this sense it's similar.
Okay, so let me understand. What other lemmas were used here? Are these other lemmas here?
It's an axiom.
Now this is expanded, so it only should contain axioms. So every node here doesn't have a proof on its own. It's just like a substitution, pure substitution that takes arguments.
So this picture, one of these has its own such picture, right? So if I take one of those nodes like AX-A,
that's not going to work. You have to, it's not a theorem. So you just take itself and ask for its statements. And one of those statements has an XA there. Yeah, similarly to this one. And you do the similar cases. It's just not a theorem, but an axiom with the name. Or you even don't have to do axioms, they have keys.
Just axiom like this?
Yeah, for example.
Okay, so now why can't I take AXA?
Oh yeah, statements and bracket XA, that's it. And it's going to contain a statement.
Where
Anywhere. You just ask for statements and then extract this axiom as a key because it's an association. Yeah, so the second argument is going to be this statement, just a list of constants and variables.
Okay, so if I say, oops,
Just two.
and I say string join of that.
Yeah.
Okay, okay, nice. But so how do I get? So that has coming into it term A, term C, term D, et cetera, et cetera, et cetera.
Yeah, it means that.
So this is basically just a somewhat daggified version of the expression tree for L1. Right, so if I were to do the same thing for L1,
Second one.
oh, I have to take part 2 here. Is that right?
Not here. After the L1.
Okay, all right, fine. Okay, so that thing has certain arguments, and that thing would elide, this whole thing would elide down to this, right?
We're going down to this.
Well, I mean, if this is used, if L1 is used in another expression, I will just
Yeah.
see a single dot there, and it will expand up to this whole thing.
Right. Yeah. So yeah, if you like find maybe T1, for example, try MetaMath proof of T1 and ask for a graph, not expanded graph, or a tree. Just tree.
T1.
Of T1. Yeah. And don't remove the reverse graph. Reverse graph. Making it a graph. So here you have like lemma 12 there. It's not lemma 1.
Yeah,
It
okay.
could be lemma 1. And it can expand to another tree there. That's what expanded tree does.
Okay.
It will expand all of those two.
Okay, so how do I get the?
Don't try it because it can go deep.
Okay,
Actually, maybe not. You can try it.
Well, what happens if I just say graph?
You can.
Okay, but expanded graph will now expand those nodes. Is that
Yeah.
correct?
Right.
And it gets very big, probably,
Yes.
because it's expanding all the way.
Yeah.
Okay, and that expanded graph is the pure substitution equivalent of find equational proof. In other words, without co-substitution.
Yes, without.
This just crashed. I'm gonna go to sleep. But I mean, okay, so this is this
I
is
have 10 minutes until my solutions.
oh gosh, okay, we need to let you get your breakfast or whatever. This is the equivalent of let's see, this is the equivalent of the substitution-based analog of the find equational proof result. Pure substitution-based analog of the find equational proof result. So in other words, MetaMath doesn't know about co-substitution, correct?
Right. There's no such thing. Just substitutions.
Okay, so it's the direct analog. So this is the single path. This thing would give us the single path version. That was the thing we were trying to generate at the beginning, where we were just treeing out all the things from the Boolean algebra axiom. We were treeing it out, but this would be a single path through that would give us the result, as opposed to the full treeing out, which is hopelessly complicated.
Yeah.
Now, the point here is that these, so what's happened here is that these lemmas are being named. I mean, that's the main thing that MetaMath is doing. That isn't just follow the axioms, so to speak. It's naming lemmas. So MetaMath is taking clusters of nodes and naming them as named lemmas, named theorems or something, right? Is that a fair statement? So in other words, there is a full graph. This is a slice of a full graph, but this is also doing this hierarchical thing, right?
Yeah,
Not only
grains.
Right, is it picking a particular quotes path through metamathematical space. It is also describing the path using coarse graining.
Is it an observer?
Effectively, I mean, it's annotating, i.e., it's annotating raw metamathematical space with named chunks.
I see. So it's putting up little signposts along.
Yeah, which is essentially what we're saying then when we go further down, we deeper still to the combinators, this is what we're going to do again.
Right.
Except the level of combinators, there's really nothing there. There are no operators, there's just nothing.
Indeed.
And I think that's where we leave it for tonight. All right, great progress, guys. A few things, and then just like.
Well, this provides plenty of material for the blog.
Yeah, it does, and I'm ready to write a bunch of stuff here, I think.
Okay.
I just have to. Yeah, I'm ready to write some stuff. Now we've got that slot on Thursday that is currently still listed as the General Relativity live stream, which we could take over and do another, if Nick is available, we could take it over and do another iteration of this. But I mean, yeah, that's tomorrow is another day, so to speak. I mean, I think this is now understanding. I mean, we need to know what we're going to get from MetaMath from this sort of signposting story. I like to understand that. Okay, and then we also got to try and think about the sort of homotopy type stuff in the univalence axiom and how that relates to all of this. That's a James kind of question.
Yes,
how does univalence relate to this?
But Nick has some insights about that too, though. Nick's also interested in univalence. Yep. We'll both be excited to talk about it.
All right, okay, fine. All right, gotta go.
So, okay, yeah, we're having this Wolfram Physics Project meeting tomorrow. Yes.
Yeah, but that's yes. Yes, that's a quite separate thing. Let's let Nick go. And we need to go. I need to go. You need to go. All right, to be continued.
Cheerio. See you
Okay.
tomorrow.
See you.
Good night.
Okay, bye.
Good night. Good